Hi students, today we will focus on elementary number theory and proofs and also visit the division algorithm and the Euclidean algorithm. Um, Hi, the first learning outcome will actually focuses on nature of mathematical proof. Okay? A statement in maths is actually a sentence which has to have true and false, but not both. So a mathematical sentence is either true or false. So for example, 3 plus 5 equals to 4, which we know it's incorrect. So therefore it's a false statement. 2x plus 3x is obviously 5x. So therefore this mathematical sentence B is actually true. Negation. Negation simply means that a statement is being negated by, for example, for A, 3 plus 5 does not equal to 4, which is actually true because 3 plus 5 is actually 8. So we add a negation by, normally we add it does not equal to something. Same goes for 2x plus 3x is actually 5x. We know it should equal to 5x, but if you add a negation to it, does not equal to 5x, it changes the statement from true being false. So by doing negation, you can actually change the truth of a sentence. So for example, 3 plus 5 equals to 4 was actually false. By adding negation, it becomes true. Same goes with the sentence in B. 2x plus 3x is 5x was true, but by adding a negation to it, you actually change the true to be false. Compound statements. Compound statements can be formed by combining them in various ways. So the most popular words that we use to combine mathematical statements are and, or, if, then. So for example, 3 plus 5 equals to 4 and 4 plus 5 is larger than 10. So both of these statements, the first one, 3 plus 5 equals to 4, is actually false. And the second statement, 4 plus 5 larger than 10, is also false. So both of them are false. Therefore, the final conclusion is also false. Okay? And for the term or, 3 plus 5 equals to 4 or 4 plus 5 larger than 10. In this case, both of these statements are false. So the final conclusion, they are false. Okay? So for example, the word if and then, if 3 plus 5 equals to 4, which we know is not true, then 4 plus 5 is larger than 10. So this statement, it becomes true. So by adding if and then, also you can change the truth of a statement. So these are some of the related implication symbols which we will use throughout the proofs chapter. Okay. This symbol simply means for all values of x. Okay, and this upside down E, yeah, it means that there exists an x. Okay, and the most popular symbol is this arrow. Okay, arrow which actually represents the implication symbol, and the if symbol, meaning if and only if. So this symbol here represents if and only if. So we will use these symbols again and again in the coming slides. Yeah, so please pay attention to the symbols. For example, there are several ways to actually do a mathematical proof, and it must be supported with logical steps and clear explanation. So every single proof must have an implication which represents a true or false outcome. Yeah. So for example, if x is larger than 5, then 2x is larger than 10. So for this statement, obviously this statement is true because if x is larger than 5, so for example, x is 6. So 2x will be 12. So obviously 12 is larger than 10. Okay, this is true by solving this inequality. So when you solve 2x larger than 10, so definitely your x is larger than 5. So this indicates that x being larger than 5 will actually result in true x being larger than 10. So therefore, this particular statement 1 is true. The next statement is, if x squared is 25, then x is 5. So if you think of this statement logically, this statement is obviously false, simply because if x squared is 25, then there's a possibility of x being positive 5 and also negative 5. So in order to show that this is false, you simply solve x squared equals to 25, and you will get x being plus minus 5. So therefore, x being 5 is not the only answer for this statement. So therefore, this particular statement is actually false. Okay. So how do we use this implication symbol? Implication statements are often called with if and then. So if and then statements are implication statements. Yeah. And how do we actually write them out using the implication symbol? The first example will be actually this. That means if and then can be represented with the implication symbol. So when this implication symbol, you should simply read it out as, if x is larger than 5, then 2x is larger than 10. For the second example, is also similar. If x squared equals to 25, then x would be 5. And then you can actually make a conclusion whether it's true or false. So how do we actually find the converse of an implication? So if statement P, then statement Q, right? Then the converse would be written as statement Q, if statement Q, then statement P, because it's the converse. Okay, that's the guide to write converse statement of an implication. So for example, this statement, x being larger than 5, if x is larger than 5, then 2x is larger than 10. And obviously we know this is true because we have explained that in previous slide. Yeah. So the converse of this statement, using this guide of writing the converse statement of an implication, it will simply be, we will need to swap the statements. So statement Q comes first. So therefore, if 2x more than 10, then x will be larger than 5. So you have seen we have actually swapped the position of the statement, right? And this is still true. Okay. So therefore, this is how you actually write a converse of an implication statement. Yeah. So next statement, the same statement with the previous slide. If x squared is 25, then x equals to 5. So the converse of this statement would be, if x equals to 5, then x squared equals to 25. But writing a converse at times can actually change the truth of the statement. It can be true or false. It can swap the truth of a statement. Yeah, so please pay attention. So why is this true? The second converse statement is actually, when x is 5, then definitely x squared is 25. There's no doubt to it, and it has to be true. The first one is false. The statement is false. Statement 2, simply because I've already explained in the previous slide. Yeah. To prove an implication is false, it is often necessary to give a single counterexample. So a counterexample simply means that you give an example that actually proves that a particular implication is false. So you just have to provide an example. So for example, for the second statement, if x squared equals to 25, then x is equals to 5. So this statement is false. So the proof will be, the counterexample here is x equals to negative 5. So this statement is false because the possible x value is also negative 5. Okay, two-way implications or equivalence. Yeah. So if P, then Q. And if Q, then P are both true when we can say P is equivalent to Q. So in this case, there's another alternative. P if Q, IFF here means if and only if here. Okay, and you can use this notation, which is if and only if. This represents a notation as I showed in the earlier slide here. Okay, next, in the first example just now, x is larger than 5, then 2x is larger than 10. And this works both ways, and both ways are both true. So therefore, you can conclude the first statement just now can be written as x being larger than 5 if and only if 2x is larger than 10. But you cannot conclude this about the second example, because when you wrote the counter example of the second example, it actually changed from false to true. So we cannot indicate that if and only if for that particular second example. Okay, now we are going to look at how do you actually write a inverse, converse, and contrapositive if you are given a mathematical statement. So this mathematical statement is stated as if triangle ABC is right angle. So we have got two parts to this statement. If triangle ABC is right angled at C, then the second part of it says then C square equals to A square plus B square. So we have two parts to this mathematical statement. That's why it's an implication statement which has if and then. Okay, so now we're going to write the inverse of this statement. Because it's an inverse, so therefore C square does not equal to A square plus B square. So this is the inverse of this statement. The converse is simply C square equals to A square plus B square, then triangle ABC is right angle at C. So what we did, the converse is similar to the previous slide. So we actually just swap the two statements around. We've actually swapped these two statements around in order to create the converse. Okay, in order to create the converse here, right? And by using of course, the word if and then. Pay attention to the word if and then. So that's how you actually write a converse. A contrapositive here is simply when you actually add negation to the converse statement. So what we did here was you have equal to here in your converse and is right angled. Alright, so what happened here is we actually swapped it to, we negate it. C squared does not equal to, and ABC is not right angle. Keyword here is not. So we have actually added negation to the converse and it becomes the contrapositive statement. So if the implication is true, then the contrapositive is always true. Okay, but the inverse and converse need not to be true. That means if the implication is true, right? Say for this implication is true, so the converse and the inverse not necessarily has to be true, but the contrapositive must be true all the time. So in this case, when you write a statement, when you're given a mathematical statement, you're required to write inverse, converse, and contrapositive. Please bear in mind of this particular tips, yeah. All right, so always remember the contrapositive must be true. Provided the implication was true, then the contrapositive must be true, but the inverse and converse not necessarily has to be true. So bear in mind, it's a very important tip, yeah. Next, we are going to focus on direct proof. So direct proof here simply means that you are actually using mathematical direct proof in order to prove a statement, whether it's true or false, or whether it's a mathematical or algebraic calculation which requires proof. So for example, prove the following universal statement, yeah. For all integers n, 4 multiplied by n squared plus n plus 1 minus 3n squared is a perfect square. Alright, so the proof is stated So when you need to prove such mathematical algebraic related proof, of course you must show some algebraic working, right? So for example, let n be any particular number, or let n be any integer. Okay, so we don't use decimals. Most of the time we use integers, yeah? And you're supposed to show that the 4n squared plus n plus 1 minus 3n squared is actually a perfect square. So you have to find a way to factorize it and show it's a perfect square for all values of n. So what we're going to do here, we're going to try to factorize 4n squared, 4 multiplied by n squared plus n plus 1 minus 3n squared. So we expand it, rearrange it, and we try to factorize it. So now for n plus 2 square, obviously this is a perfect square, right? So we have kind of like have proved the statement, but you need to write out a concluding statement usually. So what you need to do is n plus 2 will be a perfect square for any integer of n. Okay, so therefore this proof is complete, right? So you can think, if n is an integer 1, 2, 3, -1, and whatever, so on, any whole number, right? So when you substitute any number as n into here, and when you square it, it's definitely going to be a perfect square because it's squared, right? So therefore, this completes this particular proof. Okay, so these are called direct proofs. So direct proofs can come in varying ways. It can be algebraic, sometimes it's logical. Yeah, so you need to think, but you need to write your proof in terms of mathematical statements or calculations. Yeah. So now we will look at some more indirect proofs, which we're going to learn about proof by contradiction and contrapositive, but we'll focus more on contradiction here, yeah. So now we will visit the one of the method of indirect proof, which is proof by contradiction. Sometimes some mathematical statements can be quite tricky to actually using direct proof. So we need to use the indirect proofs like contradiction. So before this, we have done direct proofs, okay, like the Pythagoras theorem just now and so on. So in order to prove an implication, if P then Q is sometimes difficult or impossible to directly prove. So we need to use contradiction method. Okay, in this case, contradiction is, or you can use contrapositive, yeah. So the contrapositive negation here simply means if P then Q, or if Q then P. All right. So the not Q and then if not P is true, so P is if P then Q. So this simply it might not mean so much to you now, but I will try to use an example in the next slide to actually explain to you. So for example, if you have proof a plus b over 2 is more than and equal to surd of ab for all values of a, and b is actually element of a natural number, yeah. Okay, so for example, assume you have to make an assumption, right? You have to make an assumption. So your assumption will be always the opposite of what the proof requires. It's called a contradiction for a reason. So you start off by contradicting the original statement. So when you want to contradict larger than and equal to, the contradiction of it will be less than. That's why this method is called contradiction. Okay, and so over here is just algebraic. So once you get the contradiction, now what you're going to do, you do a contradiction and then you prove the contradiction is actually false. Therefore, your original will be true. So that's why it's called method by contradiction. All right. So first step, you contradict your original statement. All right, and then you try to prove that it's actually wrong. So in this case, what I did was I brought the 2 up, and then to get rid of the surd, I have to actually square both sides. So when I square both sides, I actually get this, or I expand it, I got this, okay, and then I tried to bring it over for AB over and try to factorize it. when I try to factorize it, I actually got a minus b squared is less than 0. So this simply shows that a minus b less than 0 is obviously false, right? Because if a and b, is any value and b is an element of natural numbers, then obviously a minus b squared cannot be less than 0. It has to have a value which is it has to be positive value, because a minus b squared is definitely, for any value of a and b, is obviously a positive value. It should be higher than 0. So therefore this statement is actually false. So therefore, since the contradicting statement for the original question is actually false, so the assumption is actually false, right? The contradicting assumption is actually false. So therefore, or hence, your original statement. Okay, so for the next example, we're going to look at proof that the set of primes is infinite. So prime numbers are basically the numbers that you can actually divide by itself, and also number 1. Yeah, so those are prime numbers, and you have to prove that the set of them are actually infinite, okay, or infinite. All right, so you can't prove this directly, all right? So you have to use some mathematical proof. So in this case, I actually wrote as, suppose the set of primes is finite having n numbers. So example, it will be P1, P2, P3 up to Pn. We don't know what n is, right? So hence a number exists that is the product of all the primes, okay? So example, I'm assuming that the set of primes are actually a product of prime. So I'm taking that as n. So a product of prime numbers will be obviously P1 times P2. It's a product, so it's a multiple, yeah? P1, P2 times Pn. And next, now you have to consider the number after n. So the number after n is obviously n plus 1. Means like the 5th term, and then the 6th term will be 5 plus 1. That's what it means, okay? So n plus 1 is obviously the product of n plus 1 prime numbers will be P1, P2, P3, and so on. And obviously it will be Pn, and always there'll be a plus 1 at the end because it's n plus 1. So if we attempt to divide n plus 5 as n plus 1 with any of the known primes between P1 and Pn, when you divide, obviously because it's n plus 1 divided by any other prime number, so obviously you will have a remainder of 1 always, okay? So therefore, n plus 1 you cannot divide, it's not divisible by any prime number greater than 1 apart from n plus 1 itself, because n plus 1 divided by n plus 1 you will get 1, okay? So therefore, so prime number is greater than the largest prime number Pn. So therefore, the supposition or the contradiction which we make is actually false. And this proves that the sets of primes are actually infinite. So the contradicting is false. Therefore, the original, which is proof that the set of primes numbers are infinite, or P1 times P2 times P3 Pn, are actually a finite set of numbers. Okay, hence the set of primes is actually infinite. Okay, so the next example here will be proof that set 2 is irrational. So what are irrational numbers? Okay, so there are a lot of mathematical terms involved here. If you're not sure, please look up for what these terms actually mean. Yeah, textbook is a good source of information, or you can actually just use Khan Academy or Google what irrational actually means if you forgot. So I just want to explain to you, if you want to, if set 2 is irrational, and if we want to actually write a contradicting statement, or we want to suppose it, it simply means set 2 is irrational, it becomes set 2 is rational. So from irrational to rational, we are contradicting the original statement. Okay. Rational we know very well. Rational means it can be written as a fraction, right? Okay, so if it can be written as a fraction, we assume SET2 will be, say, m over n, and m over n of course should not have a common factor, means we cannot simplify it further. Okay, and if we try to square m square over n square, we square it, all right, because we are trying to get we're trying to prove that this particular contradicting statement is actually false. Okay, so we square m square n square. M square is 2n square, all right, because we square both sides. Yeah, so 2 square is 2. Okay, and then we try to get, so obviously m square is actually an even number. Why is m square even? Simply because m square here is a multiples of 2n square. 2 times any value will actually give you an even number. So m square is even here. Okay, next step, if m square is even, then m is obviously even, because if m square is even, then m is obviously even, right? And m should be multiples of 2 because it's even. That's our assumption, yeah? So therefore, if m equals to 2k, then 2n square is m square, right? That one is similar from the earlier sentence. Okay, and m square, we substitute m as 2k, we're going to get 4k square. So 4k square here should be n square, right? We should be 2k square. So this shows that n square is also even. All right, if now m square is even and n square is even, so it will definitely have a common factor of 2, right? So if it will have a common factor, but initially we claim that m and n have no common factor. So this very clearly shows that if n square is even, then using the proof above, n must also be even, right? So in this case, m and n have actually a common factor of 2. Therefore, you cannot write SET2 as a rational function, right? So this is a contradiction. So our contradicting statement is actually false. So therefore, SET2 in conclusion is actually irrational, simply because m and n have common factors. So next, now we will look at proof by induction. So proof by induction is a method where actually we prove the statements being true for 1, true for k, and then we prove it's true for k plus 1, and then we conclude because it's true for a particular set of integers of 1, k, and k plus 1, and then we prove that for every succeeding value, that particular mathematical statement is true. So therefore, we can conclude if the statement is true for 1, and if it's true for k and also true for k plus 1, therefore the statement is true for all integers of n or all values of n. So for example, um, proof by induction, proof that the sum of r between 1 to n, all right, is half times n multiplied by n plus 1, and you are given sum of r is actually represented by 1 plus 2 plus 3 and so on. It becomes n minus 1 plus n. All right, so for in this case, the steps are quite fixed. We have to prove for n equals to 1, n equals to k, and n equals to k plus 1. So we have to do for 3 succeeding values. All right, so for the first part A, proof is true for n equals to 1, as I said just now. Yeah, so for n equals to 1, we sum for when n equals to 1, we have to prove both sides. So first we start off with the left hand side. All right, we start off with the left hand side. So for the left hand side, is the focus is this one for the left hand side. So when n equals to 1, the first step, sigma of r between 1 and n is simply based on this, you got to substitute your r as n. All right, and here is obviously n is 1. All right, so sum of 1 between 1, n is 1. You see n is 1 over here. pay attention, make sure you have to use the correct notations. A sum for r between 1 to 1 is obviously substituting n as 1, right? And it will obviously result in 1, right? And then we will focus on the next step here. The next step, we will actually focus on the right hand side of the equation, right? So that would be substituting n as 1, right? So it will be half times 1 times 2, right? We will actually get 1. So when you substitute n as 1, the left hand side value, which is sigma of r or sigma of any other function given, okay, should equal to the right hand side by substituting n as 1 as well. So if it's 1 and 1 here, so this simply means that the statement is true for n equals to 1, right? So the statement, hence the statement is true for n equals to 1. That is the first step for proof by induction. Your next step here would be you have to make an assumption for the part B. You have to assume that your statement is true for n equals to k. Alright, and k is always larger or equal to 1. Okay, we don't do for k equals to 0. It's always 1, 2, 3, and so on. So in this case, because n is an integer, so integer, and we only work with n being larger or equal to 1, positive integers only. Okay, so sigma of 1, now your n has become k. Please pay attention to the correct notation, yeah? So your n has become k. Okay, so in this case, you look here, your n is substituted with k. N here has become k, yeah? Okay, so sum of 1 to k for r equals to half times, so we are substituting n as k. So half times k plus 1. So this is just an assumption, so you leave it like that and you assume it's always true for n equals to k. And this is useful in part C of the solution. So for the part C, alright, we will consider n as k plus 1. So for k plus 1, so we have considered for n equals to 1, we have considered for n equals to k. Now we need to consider for n equals to k plus 1, the successive value, yeah? So for n equals to k plus 1, we got to show that sum of 1 and n here, you see n here is already substituted with k plus 1. You see the n here, substituted with k plus 1. Okay, all right. And sum of r, it remains because r is the formula that we are actually focusing on to prove. And then we are substituting n as k plus 1. So k plus 1 multiplied by k plus n plus 1. All right. This was n. We have substituted n with k plus 1. Okay. So we need to prove this. So how are we going to prove that? Simply, so this is our goal, yeah. Just bear in mind this is our goal. So in order to prove this, I've copied the goal again over here. So this was the goal. We copied it from the previous last line. All right. So next, what we need to do, we need to work out how to actually achieve this goal. It will simply be sigma of 1 to nr. This was given, right? So sigma of 1 to k plus 1 here simply will be, it's like if you have sum, if you want to find sum of 7 terms, it will be like you look for sum for 6 terms and then you add the 7th term individually. So example, like if you're going to add total sum of 6 terms is equivalent to sum of the first 5 terms at the 6th term. That's what we are doing here. So we are representing the 6 terms as k plus 1 and the 5 terms as k. So for example, we will break it down to sum of 1 k will simply 1 to k plus 1 will simply be sum of 1 to k plus with the individual system, which will be k plus 1. That means you're substituting the r as k plus 1 here. Okay, so if we expand this further, we are going to get half times k plus 1. So this one, sigma of 1 to kr is actually given over here, right? So we substitute n as k, which was the proof and the assumption we did in the step B. Okay, so we copy this down here. This is the answer in part B, right? And then this is k plus 1, which we copied down earlier from the first step. K plus 1. Okay, right? So now we need to simplify this and achieve our goal. So we refactorize this. I expanded it. Okay, I want to achieve my goal. This was my goal. My goal earlier. I want to achieve my goal. I want to prove that sum of 1 to k plus 1 for r is similar to my goal. So in order to do that, simple algebraic expansion, rearrange. Okay, what I did here, I brought half out because the goal has half as well. I try to bring the half out. So when I bring the half out, k plus 1 automatically becomes 2k2, so that when I factor in the half, I will actually get back what was the earlier line. Okay, half times 2k is k, and half times 2 is 1. Okay, and the next step here would be factorizing this, simplifying it and factorizing this. If you realize, this is exactly same as the goal. K plus 1 and half times k plus 1, and this is obviously k plus 2. Right? So since we have achieved the goal, okay, now we're going to look at the second example, where actually you're supposed to prove by induction n cubed plus 2n is divisible by 3 for all positive integers of n, or n being larger or equal to 1. Okay, so the first part, again, we'll repeat the same procedure. Proof for n equals to 1, n equals to k, and n equals to k plus 1. The three successive values we need to prove. That's the method of proof by induction. So the first part A, prove true for n equals to 1. So we will simply substitute n being 1. And if n is 1, then n cubed plus 2n is obviously 3. And 3 is obviously divisible by 3. Yeah, because 3 divided by 3 is 1. Okay, so it's true. And then for the next part, we make an assumption is true for all values of n equals to k, right? And so when we substitute n as k, it simply becomes k cubed plus 2k equals to 3n. We are writing 3m because we don't know it's a multiple of 3. We only know it's a multiple of 3, so we assume that it's 3m. And m is obviously a natural number, yeah? Okay. Next, we need to consider the third successive value, which is k plus 1. So when we substitute n as k plus 1, it will simply means it's a multiple of 3. So there's a 3 here. And n becomes k plus 1 cubed plus 2 times k plus 1. So we need to prove that when n is k plus 1, n cubed plus 2n is still a multiple of 3 in this goal form, the goal that we have it over here. So in order to prove that, we are going to substitute n as k plus 1 into the n cubed plus 2n function. So we substitute, we expand it, and we need to show that this is actually multiple of 3. So when we factorize this function, we actually determine that it is actually multiple of 3 simply because k cubed plus 2k, right? This part here is quite clear. It's multiple of 3, k squared plus k plus 1. This is quite simple. But k cubed plus 2k is actually multiple of 3 simply because we have to look at part B. It is k cubed plus 2k is actually 3m. Alright, because there's no 3 attached to k cubed and 2k, but earlier we have made an assumption that it's actually multiple of 3, so therefore k cubed plus 2k can be substituted with 3m. So 3m and 3 times k squared plus k plus 1 are both multiples of 3. right? So we can factorize it together. So therefore, this actually proves and matches the goal. So your conclusion, you can write your conclusion in this way. The statement is true for n equals to 1, and it's true for n equals to k, and it's true for also n equals to k plus 1. Therefore, by induction, it is true for all positive values, positive integers of n, or you can simply write n being larger or equals to 1 because it simply means the same. For next example, proof by induction, prove that 2 to the power of n is larger than n. So in this case, part A, because it's proved by induction, so we're going to use the same method, 3 successive value, n equals to 1, n equals to k, n equals to k plus 1. So we start off with n equals to 1. When you substitute n as 1, 2 to the power of 1 is obviously larger than 1. So the statement is true. And then for the second one, we assume that it's true for n equals to k. So when we substitute n as k, we're going to get 2k being larger than k. And we are assuming this is true. And for the third part C, we consider n being k plus 1. The successive value of k is k plus 1. And when n is k plus 1, we always need to set the goal first. So we substitute k plus 1 into the original function. So it's 2 to the power of k plus 1 larger than k plus 1. So this is your goal. You need to achieve this goal. So in order to achieve this goal, since 2k is larger than k, because that is the assumption we did in part B, right? And what we need to do here is we need to multiply both sides with 2. If we multiply both sides with 2, it becomes 2 multiplied by 2 power k. It becomes 2 to the power of k plus 1 because of index law. Okay, and then the right hand side becomes 2k. And when we do this, we rearrange it. K is obviously k plus k. So we need to do some algebraic modification here. So in this case, since k is larger or equal to 1, because k is n and n has to be a positive integer, so that's why k is larger or equal to 1. And so obviously 2k plus 2 to the power of k plus 1 will be definitely larger than k plus 1. Okay, so in this case, the statement is true for the statement is true for n equals to 1, n equals to k, and n equals to k plus 1. Then through induction, it is true for all positive integers of n, or for all values of n being larger or equals to 1. So next, there's the next example of induction. Proof that sum of 1 to n and negative 1 to the power of r minus 1 multiplied by r squared is equals to the function on the right. Okay, so for this one is also proved by induction, so you need to use the 3 successive values of n being 1, n being k, and n being k plus 1. So what you need to do here is you need to prove true for n equals to 1. You substitute 1 both sides, to the left and also to the right. So when you substitute 1 to the left and right, okay, so we are going to look at the left hand side first. If you substitute r here, which is n, being as 1, so you will reduce your value to 1. And then when you substitute 1 on the right hand side, okay, and you will also get your answer will actually reduce to 1 as well. So this shows that the left hand side equals to the right hand side. Therefore, it's proven that it's true for n equals to 1. Then for the next step, you move on to the successive value of n being k. Alright, so when n is being k, so you assume it's true for n being k, so you substitute your k with 1. Alright, substitute your n with k. Okay, so in this case, your n here becomes k. Your notation has to be written accurately. Okay, and then so you substitute your k into the right hand side, it becomes k plus 1 over here, as you can see, right? And then for the next step, this is an assumption. For the next step, you have to prove it is true for n equals to k plus 1. So this is the third step. So for k plus 1, you have to set your goal. So in order to set the goal, you substitute n as k plus 1, and this will be your goal. So at the end, you need to achieve this goal. If you manage to achieve this goal for the n equals to k plus 1, means the particular function is true by induction. In this case, you need to find sum of k plus 1. Obviously, is similar to, again, to the basics. When you need to find sum of 6 terms, it's as if you find the sum of the first 5 terms and then you add the 6th term individually. Okay, so in other words, it will be sum of 1 to k, which is the 5 terms that I'm say example is the first 5 terms 1 to k, right? Which and this part here is actually already done in part B. Okay, and then you just add the individual 6th term to the sum of the first 5 terms. So for example, in other words, if it's S6 sum, right? We have learned arithmetic or geometric sequence in our previous. So sum of 5th terms is actually sum of the first 5 terms plus the U6 individually. Yeah, so this is what is known as. So next, what you need to do, you need to make sure that this addition of this red box and this green circle actually gives you the goal, right? So there's some algebraic modification required here. So we sub this from part B, all right, and then plus with this part here. So this part here is the green part, right? Okay, and then continue your algebraic simplification. Factorize it, you factorize it, okay, factorize it out, and then you bring your k plus 1 out as a common factor, okay, and then prove that it's actually exactly same as the goal. So you see over here, this is exactly same as the goal. So therefore, your final conclusion would be the statement is true for n equals to 1, n equals to k, n equals to 1, n equals to k. It's also true for n equals to k plus 1. And then by induction, it is true for all positive integers of n or for all values of n being larger or equals to 1. So another example of proof by induction here. You are supposed to prove that actually sum of 1 over sum of r square, sorry, is equals to 1 over 6 times n plus 1 multiplied by 2n plus 1. So in order to prove this, again, we're going to use the induction method, and obviously we have to have 3 successive values, which is n equals to 1, n equals to k, and n equals to k plus 1. So in this case, when n is 1, we substitute 1 on both sides. So it will be sum of r square. When we substitute r as 1, it's 1 square and is 1. And we substitute n being 1 on the right hand side, which will actually arrive to the value 1 as well. And since the values on the left and right is the same, so therefore the statement is true for n equals to 1. And our next step here would be assume the statement is true for n equals to k. It's an assumption, so no calculation is required. Just substitute the correct values. So you got to bear in mind that the value here k and n, so n is equals to k, so n is being substituted by k for r square. Same goes for the right hand side. The n here, all the letters n here actually are substituted with k because we substituted the n with k in the formula. Okay, so this is an assumption. And then your third step here would be having n as k plus 1. So to have n as k plus 1, you consider it and you actually set your goal. So how do we set the goal? We just substitute n being k plus 1 into the right hand side. Right, so n is k plus 1, k plus 2, and also 2 times k plus 1 plus 1. Okay, and we obviously simplify it, right? And do not simplify it up to like expansion of factors, but try to write it out in the simplest factor form possible, like that, like over here. Okay, and your next step here would be, so you have set your goal, so your next step is working towards the goal. Again, we're going to use the same approach, which is sum of 1 to k plus 1. We're going to use this approach of sum of 1 to k plus the k plus 1 term individually. So sum of 1 to k for r square we have done in the second step here. So we can copy this down for the first part here, sum of 1 to k for r square. So this part here can actually, this part here is actually part B. This part here is actually this part. It's the same. It's the same part. We can copy down the answer or the assumption that we made earlier. And k plus 1 square is obtained by substituting k plus 1 into r square. So k plus 1 square becomes, r square is k plus 1 square now. Okay, and then now we expand this so that we match the goal. So in order to expand, so we have copied down 1 over 6k times k plus 1 times 2k plus 1, right? And bring down the k plus 1 square, expand it, we expand it, and when I expand it, it's up to you how you're going to expand it, but always work towards the goal. Okay, so 1 over 6. So when I rearrange this, I got k plus 1 as a common factor from both, so I brought the k plus 1 out, right? And I'm left with k times 2k plus 1 plus 6k plus 1. So I need to work on the inside because I've already got a part of the goal, which is 1 over 6k plus 1, 1 over 6k plus 1. So I need to rework on this second bracket, factorize it, and match it to k plus 2 and 2k plus 3. That's our strategy. So we expand this part. So we got 2k squared plus 7k plus 6. And then when we factorize it, we actually achieve the goal. So remember, we have to work towards the goal. So we work towards the goal. Okay, right? The final conclusion here will be the statement is true for, again, n equals to 1, n equals to k, n equals to k plus 1, and therefore the induction is true for all positive integers of n, or n being larger and equal to 1. So far we have established sum for 1 is n, sum for r is half times n plus 1 in one of our example induction, and sum for r square is such. So maybe you can try sum for r cube on your own, right? And you can also identify on how to actually determine this cubic expansion. So you should try r cube, and this is actually related to sums. We have done some of sums in the previous semester. Okay, if you don't want to use induction, you got to remember all these formulas, but normally in exams we actually specify that you need to use proof by induction, so you need to know the method of using the three successive n equals to 1, n equals to k, and n equals to k plus 1 formulas. So please take next example of induction is proving that for all values of n, or all positive integers of n, 3 is this particular mathematical statement is true. So in this case, when n is 1, you substitute n as 1, you're going to get 3 and a 0. All right, so you assume it's true. Next step, you assume the statement is true for n equals to k. That is an assumption. So therefore, it's 3 is a function of k cubed minus k, because n is equals to k, and you assume it's true. And we are going to make an assumption that is actually 3a is like a multiple of 3a, can be any number, right? And next statement would be consider n is k plus 1. Okay, and if n is k plus 1, we substitute n as k plus 1, it becomes k plus 1 cubed minus k plus 1. And then when we expand it, we try to simplify it, and we actually arrive to such value. Okay, k cubed minus k plus 3k squared plus 3k. So in this case, we can see that this is actually still a multiple of 3. Therefore, because k cube minus k is actually from the second part, which is 3a, so we substitute k cube minus k with 3a, right? And the balance we factorize as a multiple of 3, and overall we can factorize the whole equation as a multiple of 3. So therefore, we are making an assumption that b is being a k square and plus k, right? And this is like 3b, so it's a multiple of 3. So therefore, the statement is true for n equals to 1, n equals to k, and n equals to k plus 1 for all positive integers of n. So just a conclusion that when you want to do proof by induction, you need to consider 3 successive values, which is n equals to 1, n equals to k, and n equals to k plus 1, and you also need to write the concluding statement, where this is a sample of a concluding statement. Okay, now we will look into division algorithm and number bases. So for example, so our fundamental theorem of arithmetic states that, for example, if it's 6 equals to 3 times 2, or 36 equals to 2 times 2 times 3 times 3, right? This simply shows that a product of prime numbers apart from the order of the primes, right? You can express it in a unique way. So for example, 430, expressing 430 as a product of prime numbers, 430 divided by 2 is 215, and then 215 divided by 5 is 43, and 43 divided by 43 is 1. So therefore 430 is simply 43 times 5 times 2, or 2 times 5 times 43. Okay, so this is a fundamental theorem of arithmetic which involves the division algorithm. Yeah. So next, now the division algorithm simply states that if you consider division, for example, 203 divided by 8, it is simply 25 remainder 3. And this division can also be written as 25 plus with the remainder over the divisor, right? So the remainder is 3 over the divisor. So in this case, when you were in when you first started learning division, right, it simply means 203, all right, okay, divided by 8 is actually 2. You get 16 here, 43, and this is 5, 40. Right? This is normal division, just to show you what is a division algorithm. And remainder is 3. So you can write your answer as 203 over 8 simply means 25. All right, 25. And then the remainder 3 over the divisor, which is 8. Okay, you can also write it this way. And next, in the context of division, 203 is known as the dividend. Okay, 8 is the divisor, and 25 is the quotient. Right, 25 is the quotient, 3 is the remainder, 8 is 3 is the remainder, and 8 is the divisor. Okay, 203 is the dividend. Okay, and the relationship between these 4 quantities can be expressed as 203 equals to 8 times 25 plus 3. I think you're more comfortable expressing it in this form rather than this form. Okay. Next, example, if we write it in terms of unknown, it will be A equals to BQ plus R. BQ here means B is actually the 8, and Q is 25, and plus 3, so plus the remainder is R. Right? So you can express it in this form, which is similar to this form. Okay. Next, this theorem is known as division algorithm, or its another name is called division identity. Right? Just bear in mind, you need to also revisit some terms like greatest common divisor. Okay, you can also write it in the form of bracket A, comma B, right? So A here will be 203, comma B here would be 8. Okay, so now we will actually look at how this theorem is being proven, right? You don't need to know the proof. This proof is just for extra knowledge, right? So I'm not going to go into the details of this proof. So for example, we will look into how this division algorithm is actually used repetitively, or it's a repeated application, which is known as the Euclidean algorithm. So you have to understand what is a division algorithm, and you need to apply division algorithm repetitively in order to solve mathematical problems related to the Euclidean algorithm. Okay, so in this case, we will look at, for example, find the greatest common divisor of 203 and 8 using the Euclidean algorithm. So basically how we're going to do this is we start off, this is the same value from the previous slide. Okay, so it's 203 equals to 8 multiplied by 25 plus 3, right? So we do the normal division. It can also be written as 203, 8, right? And then the next step here, we will actually divide 8 with 3. Okay, so it's simply 8, 3 times 2 plus 2. All right, and then next we move on. We will actually divide 3 with 2. You see the pattern is the same. So we are always taking the divisor and dividing it with the remainder of the previous working. Okay, and next step here, 3 will be divided by 2 here. So it will be 3 equals to 2 times 1 plus 1 with remainder 1. And then we will work it out till we get a remainder of 0, yeah? So it's 2 divided by 1. It will be 1 times 2 plus 0. So the remainder here is already 0. Okay, and that this shows that the greatest common divisor of 203 and 8 is actually 1. Okay, so this is one of the application of Euclidean algorithm. Next, we need to find the greatest common divisor, right, of 132 and 424 using the Euclidean algorithm. So we start off by dividing 424 with 132. So 424 divided by 132, it will be 132 times 3 plus 28. And next, we will actually move on by dividing 132 with 28, right? The quotient with the remainder again, 132 and 28. And then we'll move on. We will get 132 divided by 28 is 132 equals to 28 times 4, and the remainder is 20. Okay, so we will move on to divide the 28 with the remainder, which is 20. Okay, and then the next line here, 28 equals to 20 times 1, and the remainder is 8. And then we will divide the 20 with the remainder 8. Okay, for the next line, so 20 equals to 8 times 2 plus 4. So the pattern is same, it's repetitive. Okay, and you need to show each line of working. And the next step here, we will actually divide it with the remainder. Okay, and then here we will actually, when 8 divides with the remainder, we will get a remainder of 0. 4 times 2, 8 equals to 4 times 2 plus 0. So in this case, once you already get a 0, you know that the greatest common divisor of 132 and 424 is actually 4. Because you have no more remainder, and we will take the number that we used to divide the divisor that we obtained just now, which was 4. So the greatest common divisor for 132, 424 is actually 4. Okay. Next, we will actually look at how to actually apply Euclidean algorithm. So this is based on the knowledge from the previous slides, right? which is a division algorithm extended to finding greatest common divisor and so on. So for example, express the greatest common divisor of 132 and 424 in the form of 132s and 424t's. That's what we're trying to do. Yeah, we're going to express in terms of another two unknown. Okay, so from the previous working, we have got 424 equals to 132. Okay, this one, this simply means 132 times with 3 plus 28. And then what we do is we are going to make, for each line that we calculated in the previous slide, we're going to make the divisor as the subject of the equation. So it's 28 equals to 424, take away 132 times 3. Okay, and then same goes for the next line, right? We're going to make the remainder as the subject. Same goes for the coming line, 8 becomes the subject, and same goes for the last line and the second last line, and also the last line. 0 equals to 8 minus 4 multiplied by 2. So once you get that, now you have to work out, you get the, identify the S and the T. So in order to get that, we're going to work line by line. So your next, of course, the greatest common divisor here was identified at this line, all right? And in this case, we continue with the same working from the previous slide. And we need to identify, so line A actually, so we start off with the lowest line, with the lowest value first. 4 equals to 20 minus 2 times 8 times 2, or 2 times 8. Okay, and now we need to substitute line B into line A. Yeah, so what we're going to do here, we're going to substitute line B as 8. So line B says 8 is actually 28 minus 20 times 1. So we're going to substitute this equivalent over here. So this 8 equals to 28 minus 20 times 1 goes here. Right? So this will give you, so you see I've substituted this as equivalent to 8. Okay, and then the next step would be simply trying to simplify this, but bear in mind, when you simplify, you actually leave the multiples of 20, and you just combine the multiples, as in this is 1 of 20, 1 of 20 and 2 of 20, so it becomes 3 of 20s and minus 2 of 2 multiplied by 28, right? So don't bother multiplying it, just leave it in terms of 20, 28 and so on. Okay, simply because in the coming lines we're going to substitute. So the next line, that is C, so when we substitute line C, we have actually equivalent of 20 in line C. So 20 is actually this, right? So we're going to substitute 20 over here. Okay, so in this case, say 20 is being substituted over here, right? And then next we actually simplify. It is 3 times 132 minus 3 times 4, 12 of 28 minus 2 of 28, and then we combine the alike terms together. So 12 minus 2 is minus 14. Okay, and next, now the next line here we have 28. The next line above here now is 28, so we're going to substitute equivalent of 28 into 28 over here. So what we're going to do here is we're going to substitute the equivalent of 28 into 28 over here. So what we're going to do here is this line D to substitute for 28. So 28 goes here, 14 of 28. Alright, and then we expand it. So 3 times 132 minus 14 times 424 minus 132, and then this becomes 42 of 132, right? And we substitute it here. We collect the 132 terms together and the multiples of 424 together, right? And we will actually get 14 multiplied by we get 45 times 132 minus 14 times 44. And if you realize, this actually fulfills the question, because the question actually said we are looking for multiple of 132 and also multiple of 424. So comparatively, and 4 is obviously the greatest common divisor, right? We started off with the 4 here, right? Okay. For this next example, we are required to show that 280 and 117 are relatively prime. And for part B, we actually need to apply the Euclidean algorithm to solve, determine the value of A and B given 280 and 117 equals to 1. Multiple of A and B equals to 1, yeah? So this part A, we need to show whether that 280 and 117 are relatively prime. So for that, we actually can look for the greatest common divisor. Okay, so we start off with 280 divided by 117. So it's simply 280 equals to 117 times 2, and the remainder is 46. And then we make because later on for part B, we need to do Euclidean algorithm. So we might as well make the remainder as the subject of the equation, right? And then as usual for the next line, we simply divide the quotient 117 divided by the remainder. So it's simply 117 divided by 46. It will be 2 times 46, and the remainder is 25. And then over here we make 25 as the subject of the equation. For the next line, we simply divide the quotient 46 with the remainder 25. Okay, so it will simply be 46 equals to 25 times 1, and with remainder 21. And we make here the remainder as the subject of the equation. And for the next line, we simply take the quotient 25, divide with the remainder 21. So 25 equals to 1 times 21 at 4. Okay, and then we make 4 as the subject of the equation. And for the next line, we continue 21 divided by 4. Okay, 21 is the divisor, divided by 4 being the remainder. Sorry, 21 being the quotient, divided by 4 being the remainder. So 21 divided by 4 is simply 4 times 5 plus 1. So now we have actually got 1. So we have actually proven that the greatest common divisor is actually 1 for 280 and 117. Therefore, these two numbers are relatively prime numbers, yeah? Okay, so this is the conclusion for part A. For part B, we simply need to work towards getting multiples of 280 and 117, right? So in this case, as usual, based on the previous example, we start off with the lowest line, 1 equals to 21 minus 4 multiplied by 5, right? So we need to substitute 4, equivalent of 4 into the earlier line. So we will actually substitute 4 equivalent to 25 minus 21 times 1 over here. Okay, so when we substitute the equivalent, 5 times with 4, the 4 is this equivalent. Okay, and then the next step, we actually simplify it. Okay, we collect the multiple of 21 and 25 individually, right? And then we will get 6 times 21 minus 5 times 25. Right, so now for the next line, you actually have 21, which is the line here. 21 equals to this. So we're going to substitute the equivalent of 21 over here as 21. So in this case, this orange color is substituted as 21. 6 times 21 multiplied by 5 times 25. Okay, so we simplify it first. We have to do it step by step, yeah? So we simplify it first, and we leave it in terms of 6 times 46 minus 11 by 25. Okay, so the next step here will be substituting a line later. Okay, so for that, we have 25 over here, so we're going to 25. So you go layer by layer, you go from bottom to up, yeah, don't jump steps. Okay, so 25 is equivalent to the green color circle here. So we substitute 117 minus 46 multiplied by 2 as 25. So you substitute it and then you leave it as a multiple of the number 46 and also 117. Okay, and then for the next line here you have 46. So you're going to substitute the equivalent of 46 into this particular line, and this will reduce the line to being multiple of 280 and 117, and you have no any more lines to substitute, and obviously 280 and 117 are the question requirement because you need to find the multiple of 280 and the multiple of 117. Okay, so in that case you simplify and leave your answers in terms of a number multiplied by 280 and another number multiplied by 117 because that fulfills the question. Okay, and through observation you will obtain that your A is 28, your B is negative 67. So just compare the numbers boxed in right here. So as you compare, multiple of 280 is A, and that is simply 28, and multiple of 117 is negative 67. So please, when you compare, please consider the signs positive, negative as well. So this is a typical example of application of Euclidean algorithm. Yeah. So next here, number basis and division algorithm. For example, you have learned in high school number basis. So this simply means 2314. This simply means 10 to the power of 3 simply means 1000. So this 2314 is actually a combination of 2000 added up with 300s added up with 10 and added up with a 4. So 4 is basically 4 multiplied by 10 to the power of 0. Okay, perhaps because number base 10 is the most traditional number base being developed, I think simply because we have 10 fingers and it originated from there. And then there are so many other number bases used, which is base number base 2, 5, and so on. We will not question you this in our exams, but recommend you to actually revisit how to convert interbase, yeah, meaning how to convert base 10 to 2, base 2 to 5, or 8 to 2, and so on. It will be good for you to actually convert. So for example, if you consider the number 48, all right, what would this number be in base 5, right? So in this case, we write it out first as a multiples of 5, as in 5 power 0, 5 power 1, 5 power 2, 5 power 3, and so on. So 48, the highest power here would be 5 power 2, right? Because 5 power 3 is already 125, but our number is only 48. So 5 power 2, normally we start thinking of the highest power first. So 5 power 2 is 25. So 48 consists of 25 plus 4 times 5 power 1. Okay, how do we decide 4? Because 1 to the power 1 times 25 is 25. So 48 minus 25 is 23. So we have 23 more to fit it into base of 5. So it's obviously 4 times 5 because 4 times 5 is 20. And then we have remainder of another 3. So it's 25 plus 20 is 43, and we have remainder of sorry, it's 25 plus with 20, right? So it's 45. So 48 minus 45 is 3. So we need another 3. So 5 power 0 is 1. So 3 times 5 power 0 is actually 3. So it's 25 plus 20 plus 3. Okay, so we'll actually arrive to 48. So how do we write it out? It's actually 143, sorry, base 5. Okay, this is how you actually read it. And Normally a number from the left is 5 power 0 power 1 power 2 and so on. Okay, so please do actually revise a bit on how a number base are interchanged. And another example, if you consider 4152 base 6, what would this number be in base 10? So how do you convert any base to base 10? Base 10 is basically the numbers that we are using. So what you need to do here is you simply need to convert, like the last digit 2 here will be 2 times 6 to the power 0, and then followed by 5 to the power 6 power 1, and 1 times 6 power 2, and 4 times 6 power 3. So it's quite simple. Okay, it starts from the extreme right being power 0 and it increases to the left. Okay, and then you just use your calculator and you compute, you will actually get 92 base 10, which is base 10 is basically the numbers that we used in our daily life, just that we don't write a base 10 at the bottom because it's understood. Okay, right, so please try to actually just revisit how number bases are being interchanged and how to convert any base to base 10, and how to also convert any number which is base 10, our daily numbers, to any other base. Okay, next, another example here would be 1136 base 10 as a number of base 6. Okay, this a little bit challenging. Base 6, so we need to find the largest number first. So we need to think that 1136 divided by 6 is 189, remainder 2. So in this case, we need to keep on dividing, so we will know what will be the largest number or the smallest number. Okay, so each time here what we are doing, we are dividing the quotient with the number 6, right? So in this case it will be 5132 to the base of 6. So this is a method. How do you convert base 10 to any base 6? So if it's base 5, you keep on dividing with 5. So you can use similar method to convert all the normal numbers which we use daily, which is base 10, to any other base. Okay, so another example, if you need to express 2213 base 4 as a number of base 5. Okay, so in this case, when you want to interchange different bases, so far we have actually visited how to convert any other base to base 10, or how to convert base 10 to any other base number. Okay, now next we're going to see if we want to interchange a base like 10 to 6, 2 to 5, 8 to 2, and so on. So you can't directly convert, you need to always convert it to base 10 first as an intermediate base, and then you can convert to any other base after that. Please remember that, yeah. So for example, 22134, you convert it to base 10 first. Okay, and then next step here, you need to convert it, that particular base 10, to base 5 then. So base 10 is like an intermediate numbers, yeah. So you convert it, like I said, if you, because you want to convert to base 5, so you divide 167 with 5, and then whatever quotient you got, you actually divide it with 5 again, and this process repeats until you get a 0. Okay, so your answer would be 1132 base 5, right?